In this lecture, I will introduce the second main topic of the course, vector models. As mentioned in the last lecture, everything we've done so far was working under the assumption that beta was sparse. And this is something we'd like to get away from, or at least have an alternative to. So, take for instance a typical economic problem of forecasting GDP, which we'd like to do using many macroeconomic variables, as for instance central banks would do. It's typically not realistic to assume such strong conditions on the beta factor that would basically mean that most of these variables do not actually impact GDP, even though we know it's of course not the case. So what we will do here with vector models is to look at an alternative way to impose structure. And that is we're going to not focus so much on the betas directly, but we're going to instead focus on the axes. And what we want to impose is that the axes are generated using some common underlying structure. For instance, if we look at the macroeconomy, we can define something like a business cycle, which we know affects many macroeconomic variables. So this business cycle could be one potential so-called common factor that is generating all of your axes, that is influencing all of the explanatory variables. Well, the same thing you could think of is, for instance, something like an overall interest rate. Even though we know that in fact there are many interest rates, they will likely all move together and have the same impact on variables. So we can think of some common factor there being an interest rate. In this way, in economics, there are many things that where this factor structure seems to be a reasonable approximation. And this is therefore an alternative way to deal with high-dimensional models. Right, so let's look at the formal setup. So we take the same kind of high-dimensional regression, where x is still p-dimensional, so it's a high-dimensional object. And so now we're not going to say anything about beta, but instead we're going to say something about x. So we're going to let x be driven by common factors f. And we assume that we have r of them, where r is small. So unlike p, which can be large, r should be small. Now the way that these factors influence the axis can differ for each series. And that is the matrix lambda is going to be more or less the coefficient matrix of your factors f. Plus, this structure is not exact, so we also have some error terms new, which are going to be different for each time period or for each observation, as well as for each variable. So this matrix f, it's an n times r matrix, so n are our observations. Typically they will be, in this context, they will often be time, but do not necessarily have to be. And r are these common factors. Now, let me already mention that we do not assume that we actually observe these factors. So think again about the business cycle. This is something that is very hard to actually observe. So even if we believe it's there, how do you measure the business cycle? So in general, we do not make any assumption about that we observe these factors. And in fact, in general, we will not even make any assumptions about what they should represent. We only think that they are there and there's r of them. Of course, that also raises the question, if we don't actually observe them, how do we choose this r? So this is one of the issues that we'll have to tackle when we look at vector models. Now, as I already mentioned, we have a coefficient matrix, lambda. And this, in relation to vector models, we actually call the loadings. So they describe how much the factors load on each of the variables. So this is a p times r matrix. So the r corresponds to the r factors, and the p corresponds to the p variables in x. So the first row indicates how do the r factors load on the first variable in x. And the last row indicates how do the r factors load on the p variable in x. This can obviously be different across variables and across factors. So you can imagine, for instance, take again macroeconomics, that there might be some factors which more represent the real economy, something like a business cycle. They would load more on related variables in the real economy, whereas you might have something that's a factor which represents more the monetary part, which would load more on monetary variables. Finally, we have these error terms, these new, which we call idiosyncratic components. So these are the things that are happening in the axis that cannot be explained by the common structure. So obviously this is important to allow for these, given that we'll never have something even close to a perfect vector structure. Now again, to make sure we have all our dimensions right, x is n times p. Then f is n times r. So it is the observations, but r factors, and r being small. Then of course lambda is now here transposed, so we have lambda prime being r times p. And of course the idiosyncratic components have the same dimension as x n times p. Of course you can also write stuff for individual variables, so each xj has the same factor, because the factors do not depend on the j, or on the dimension of the variables, times the loading corresponding to that variable lambda j and the vector of error terms nu of idiosyncratic components. Or if you want to write it element by element, we can write it as in the bottom line. Now, factor models are not really new, and in principle they're also not very special. Take, for instance, in cases where we've encountered them, for instance in finance, they are very popular. The CAP-M model is a factor model. Take the return, the excess return for a certain asset J in period I, and we model that as beta J, the beta corresponding to that asset, times the market return in period I plus the idiosyncratic return. So here the market return, which is common to all the assets, is a common factor. Of course, here it's an observed common factor. While you can extend that to a very popular model in finance is the Fama-French three-factor model, where next to the market we also add the factors S and B and HML. And this has been extended to 4-factor, 5-factor, or how many factors you actually want, and all sorts of combinations. Now, if the factors are observed as here in these models, this just becomes a standard regression model. And if we want to estimate the betas, you can just estimate those in this model just using these squares. It's just a regression of your explanatory variables of your dependent variables on your explanatory variable, in this case the market return. So if the factors are observed, well, everything can be estimated with these squares. There's nothing special about it. Now, of course, the setting that we want to look at is to generalize this and say, well, these factors, we do not let them be, we assume that they are observed. Now, the goal that we have is to reduce dimensionality. So suppose that we would substitute in our regression for y the expression for x. Then what we can of course do is just plug this factor expression in, and you'll see if you write things out that, well, you get here a product of coefficients, get lambda prime beta, which you could just write as the single vector of coefficients beta f. So we could let y be written as f times beta f plus a new error term, which is composed of the original error term and the idiosyncratic components multiplied by the betas. Now, generally, of course, if your idiosyncratic components are not too large, then this whole error term will be relatively small, and you've lost fairly little in terms of explanatory power, and most of it is captured by this term f. So if you knew f, like in the, for instance, the finance model I mentioned in the previous slide, then you could directly, instead of estimating a regression of y on x, you could estimate a regression of y on f. This would just be a standard low-dimensional linear regression model, and you could just use least squares. So given that R would typically be small, all the high dimensionality would be gone, and you would do almost as well as regressing on X, but of course it would be much easier, so it would be worth it. But, well, the complication, of course, is that we do not claim to know F. And so we have to estimate the factor structure. And this is something we can do. So, of course, we have this factor structure on X, and as we will see in the next lecture, we can use that to come up with estimates for F. Now let me go to the seminal paper of Stock and Watson, or actually the two papers in 2002, where they proposed the factor augmented regression model, which is very similar to the expression we have here. So they directly move to the final expression here, right, where they don't just say first say y on x, but instead directly go to y on f, but with f being unobserved, plus adding some variables w, which you anyways want to include directly. So that would be similar if, say, you would do the lasso and you would know for sure that there are variables that you'd want to include. Well, you could always do that without just put no penalty on those variables. Well, the way we do that for the factor model is just to include those variables directly and not absorb them into our factors. So they start from this setup directly, but you can keep in mind to link it to the high dimensional regression model. We can go these steps, first regressing y on x, then modeling x having this factor structure, and you go directly, if you plug anything in, you can go to this model. Now they assume the same thing about x being generated from a factor structure, and then propose methods to estimate f from x. And what they then do is, once they've estimated it, then you can plug your estimated factor in, because this one, of course, you do have, right? You have these estimates. So this is a regression you can estimate, and this is a low dimensional regression because R is small. And this is a regression that you can therefore estimate using just, for instance, least squares estimation. Now, if you read those papers by Stock and Watson, you'll see some different notation. So let me very briefly mention the differences in terms of notation. So you see what is the link and what is the difference with their paper. So what they write is, so I wrote the model in the first line, and what they write is the model in the second line. So there are several things that are different here. First, they use T instead of I, and capital T instead of N. Now, this is not a big change. This is simply because they really look at this in a time series setting, because they really propose it from an economic point of view. Now, this, of course, is easily managed in our setup as well. We just call it I because we're not necessarily working in time series. And in fact, you could do the factor model in different settings than time series. But since they work in time series, they call it small t. Now, another thing that they have different is that they have a plus h here. So the reason why they do that is because they use it for forecasting. So they propose this model for predicting y h periods in the future using the values of the x's and w's. Now, I say x's intentionally because you use the value of the x's to get the values of the f's. Again, this is just a matter of choice, right? You can just take h equal to 0 and you would have the same periods as before. But even if you don't, the only difference is to the model as I formulated, that actually what we're using is t minus h observations. So we're not using all t of them or all n, but we're using actually t minus h. Well, the reason for that is simply, well, this is what we actually observe. We observed y1 up to y capital T, and the same for x and the same for w. But we're going to match not y1 to x1, but we're going to match y1 plus h to x1. So we have to shift everything. So we shift these, basically we're shifting these up to have y1 plus h matched to x1. But that of course also means that when we have y capital T, we need to match it to x capital T minus h, and the same for w. So we're losing h observations by shifting it like that. This is, again, is just a matter of how you want to look at the problem, and it does not really change anything in general. So if you want to go back to our framework, well, you could define a new y, say yt star, as being yt plus h, and then t star as being t minus h, to bring you back to the setting that we have been looking at. Now, there's one more thing regarding notation that I want to mention, and that is that what they write, if they look at scalar notation, they look at indices. Where we use I and j, they use I and t, but their I is actually rj. So rj is the variables, 1 up to p. Their I is the variables, and they call them 1 up to capital N. So this is a bit confusing that this I is actually rj, and this capital N is not r small n, but it's r small p. And r small n is capital T, and r small I is small t. So I can imagine that this can be a bit confusing. Unfortunately, there's no way to avoid this kind of confusions, because all the material, all the literature that we're using simply defines its own notation. So there's no way to avoid that. Now, what I'm going to do to try to make sure that we cannot actually get into confusion with the I is I'm going to avoid I now in the lectures about factor models. So what I'm going to do is I'm going to write T everywhere, and I'm going to, for the observations, and I'm going to write J for the variables. So I'm not using I because, well, I could have two meanings. So to round up, this is how I'm going to write it now in the following lectures. I'm going to write yt, and I'm going to say that t goes from 1 up to n. These are our observations. And I'm not going to be bothered by doing forecasting h periods ahead. As I said, you could just always modify the model to allow for that. It's not important when we discuss it. And also note that even though I use t, we do not necessarily need this to be a time series model. Like this could be any other model as we had before. So I'm going to write then in scalar notation t, comma j, indicating observation t, variable j. So we're not using the I at all. I am going to stick with our small n and our small p because those we have been using throughout, and I think they will also not lead to confusion. So if you ever get lost with the notation, here's a table of basically of the notations we've been using. So for observation, we had used I, where I went from 1 up to small n. For variables, we had used j, where j went from 1 up to p. I'm going to keep that notation, except I'm going to call I equal to t small t. Now, Stockholm Watson used that same t, but they use capital T, or t minus h. I'm going to call that n. And when they use I, I'm going to stick to j to avoid confusion. And I'm also not going to use capital N because that might confuse us with small n here. Well, that brings me to the end of the introduction to factor models. So what I'm going to do in the next video is discuss how we can actually estimate those factors.